Welcome to the deep dive. Today, we're looking into a pretty serious situation in aviation,
Yeah.
the emergency electrical configuration. That's the ELEC EMER config procedure for the Airbus A320 and 321.
It's definitely one of those scenarios pilots train extensively for.
Yeah, and we're planning to go beyond just the checklist today. The goal is to really get into the manuals, understand the technical trigger, what actually causes this.
And the limitations, too. They're severe.
Exactly. The limitations it puts on the aircraft, and crucially, the kind of operational mindset pilots need to adopt to handle it safely. It really feels like a test of the human element when the tech fails.
It absolutely is.
Okay, let's unpack this. Maybe start with the absolute trigger. What sets this whole emergency state in motion?
Right. So the ELEC EMER config, it isn't just like a minor power flicker. It's very specific. It's defined as the loss of supply to both the AC1 and the AC2 bus bars simultaneously.
Okay, AC1 and AC2 bus bars.
Yeah.
For those of us not deep into aircraft electrical systems, are these basically the main power hubs for almost everything?
That's a good way to put it, yeah. Think of them as the primary distribution points. They power your main flight computers, navigation systems, most hydraulics, environmental controls. Basically, the works.
So when they both go dark.
It's catastrophic. The aircraft immediately enters this emergency state.
Yeah.
And the first thing pilots do is grab the QRH, the Quick Reference Handbook, for the procedure.
And I imagine the plane itself reacts instantly.
Oh, yes.
Yeah.
Automatically. The loss of those two buses triggers the immediate extension of the ram air turbine, the RAT.
Ah, the RAT, that little propeller that drops out. It always looks sort of surprisingly low-tech, but incredibly vital. How does it generate power?
It's clever mechanical engineering, really.
Yeah.
The RAT drops into the airflow, the wind spins the propeller,
Okay.
and that mechanical rotation powers the blue hydraulic system.
Mm-hmm.
That hydraulic pressure then drives the emergency generator.
So it's hydraulics driving electrics?
Exactly. And that emergency generator supplies a very specific, isolated part of the system, the AC Essential Bus and the DC Essential Bus, AC/DC ESS, BUS.
That's the lifeline, then. The absolute minimum needed to fly.
Precisely. Just the critical flight instruments and essential controls. Nothing more.
Okay, so you're flying on this already powered emergency generator, but like any turbine, it needs airflow, right? What happens when the aircraft slows down, maybe for landing?
That's where things get very critical with speed. The RAT needs a certain amount of airflow to generate enough hydraulic pressure.
There's a minimum speed, I assume?
Yes. If the aircraft speed drops below 100 knots, the system automatically switches power generation from the RAT to the aircraft's batteries.
Okay, so batteries take over, but batteries don't last forever.
Not at all. That switch significantly cuts down your remaining flight time, and there's another threshold. Below that 100 knots, the DC BUS connects to power essential DC items.
Right.
But if you slow down even further, below just 50 knots, say, during the landing rollout, the ACESS BUS itself is shed. It disconnects.
Wait, the essential bus, the lifeline, it just goes away.
It does. And that means losing more critical components, specifically FAC1 and FDC1.
FAC1, flight augmentation computer, and FMGC1, the main flight management computer, losing those at 50 knots. What does that mean practically?
It means a significant loss of computational help. FAC1 handles things like yaw damping, flight envelope protections. FAC1 is your navigation brain, flight path calculations, auto thrust.
So you're truly flying by hand at that point?
Very much so. Basic instruments, manual thrust, direct control inputs. By this stage, the ECAM system has been shouting land ASAP for a while.
And they've declared Mayday.
Absolutely. You simply cannot sustain flight safely in this configuration for long. It's an immediate landing situation.
Okay, so the automatics are trying to manage this, the RAT deploys, power switches, but what if things don't go smoothly? What if the emergency generator, say, doesn't come online as expected? Are there manual steps?
Yes, the QRH covers that. If the automatic attempt fails, the crew has to manually troubleshoot. First step is cycling the generators, turn them all off, then back on one by one, trying to reset them.
A sort of turn it off and on again approach?
Kind of, yeah, but very deliberately. If that doesn't work, the next step is crucial. Set the BUS tie push button, switch to OFA.
Bus tie off.
Yeah.
What does that achieve?
It isolates the electrical channels. It prevents a fault on one side, potentially affecting the other. It's trying to contain the problem.
Like electrical quarantine.
Exactly. And if that still doesn't stabilize things, there's one final major manual action. Set the EMER mode cell switch to man IGN.
Manual ignition. What's the implication there?
Big implications for fuel. It means the engines are now being fed purely by gravity. All the electric fuel pumps are off.
Gravity feed only. Wow. Okay. This is where it gets really interesting because flying in this state isn't just about managing the electrical failure. It fundamentally changes how the aircraft flies, right? The constraints become physical.
That's absolutely right. The aircraft becomes a different beast. The first major constraint governs your whole flight profile. You must maintain a minimum rat speed, Minian rat speed of 140 knots.
140 knots minimum. Why that specific speed?
That's the lowest speed guaranteed to provide enough airflow for the RIT to spin fast enough to power the emergency generator via the blue hydraulics. Drop below that.
And you risk losing even that essential power, forcing the switch to time-limited batteries.
Correct. And pilots are warned, even at 140 knots, the RIT might struggle to supply the generator during the flare just before touchdown.
So a minimum speed. Is there a maximum speed too?
Yes. Speed is capped at a maximum speed of 320 knots.
Why the upper limit?
It's because you've lost your normal flight control laws. Those sophisticated computer protections that prevent overstressing the airframe, overbanking, high G loads, they're gone.
So the 320 knots is a structural or control limitation.
It's tied to the degraded flight controls. Once you lose the normal laws, especially when the landing gear is extended, the flight controls revert to direct law.
Direct law, that sounds basic.
It is. Side-stick inputs translate directly to control surface movement. There's no computer interpreting or limiting the inputs, no protections.
So raw flying skills become absolutely critical.
Paramount. You have to fly it smoothly, precisely. It requires a very different touch than pilots are used to with the normal protections active. Treat the controls with a lot of respect.
Okay, what about the APU, the auxiliary power unit? Can that help restore some systems, provide more power?
It can, but there are significant catches. First, you have to wait. You cannot attempt an APU start for 45 seconds after losing both engine generators.
Why the delay?
Potential interference with the emergency generator trying to connect. The system needs that brief window clear.
Okay, 45 seconds. Then what?
Then, you can only attempt to start the APU if you're below flight level 250, that's 25,000 feet.
So if this happens up at cruise altitude, say FL 370.
You have to descend first. Get below FL 250 before you can even try the APU, all while maintaining that critical 140 knots minimum speed. It adds another layer of complexity to the descent planning.
Right. Let's talk specifics then. INOP SYS lists the systems that are just gone. This must drastically impact approach and landing planning.
It's a long list, and yeah, the impact is huge. Take braking, for instance. Anti-skid system, inoperative, gone.
No anti-skid. Okay, that sounds tricky on landing.
Very tricky. And because anti-skid is out, the maximum available brake pressure, max BRKPR, is limited to just 1,000 psi, mechanically limited.
1,000 psi. How does that compare to normal braking pressure?
It's significantly less, dramatically less, which means your landing roll distance increases substantially, especially on a wet or contaminated runway.
How do you even steer during rollout with limited braking and no anti-skid?
Carefully. You have to rely on differential braking using the rudder pedals to apply brakes individually to the left or right main wheels to maintain the center line. It demands fine footwork.
And that's compounded by losses in flight controls too, right?
Yes. You lose specific spoilers, numbers 1, 2, and 5 are INOP. You also lose certain channels of the flight control computers, ELA, SEC, SFCC. This affects roll control, damping, overall stability.
What about navigation? With FMGC1 potentially lost or degraded?
Navigation planning gets tough. The FMS predictions for range, fuel, arrival times, they become unreliable. You can't trust them.
So manual calculations, estimations?
Pretty much. And you have to factor in that fuel consumption is increased in this configuration. The aircraft isn't flying as efficiently. It all points back to that land ASCP instruction, get on the ground.
And more landing challenges.
Oh, yes. Nose wheel steering, NWS, is unavailable.
So after you stop, you can't paxi normally?
You can't steer with a tiller, no. Only differential braking very carefully to maneuver, or you wait for a tow.
Yeah.
Also, thrust reversers are unavailable.
No reversers, limited brakes, no nose wheel steering. Landing sounds intense.
It is. And remember the fuel situation. Gravity feed only. GRVTY fuel feeding is enunciated.
Right, because the pumps are out.
Which means pilots must absolutely avoid negative G factors. Any maneuver that could cause fuel to momentarily float away from the engine inlet lines in the tanks could lead to a flameout. Keep it smooth. Positive G.
It sounds like you can only use wing tank fuel, too.
Mostly. Center tank fuel can only transfer by gravity, and the last 2 tons or so in the center tank are basically unusable. Another planning factor.
Okay, we've painted a picture of a severely degraded aircraft. Let's shift to the cruise mindset. How do they manage this? You mentioned the golden rule.
Exactly. When things go this wrong, you fall back on fundamentals, the absolute bedrock principles.
Rule number one.
Fly, navigate, communicate, in that specific order. Always. Pilot flying, PF, focuses on keeping the aircraft stable and flying the intended path. Pilot monitoring, PM, handles communication and checklists. Clear task sharing is vital.
Fly the airplane first. Makes sense. What else?
Use the appropriate level of automation, which in this case might be very little, but use what you have correctly. Third, understand the flight mode enunciator of the FMA at all times. Know exactly what the autopilot or flight director is doing, if anything.
And the last rule.
Take action if things don't go as expected. Be proactive. Don't just passively watch something go wrong.
So the ECAM alert comes up. Alarms are going off. What's the workflow? How do they process this, especially since it requires an immediate diversion?
It follows a standard flow. First, perform the immediate ECAM actions. The PM usually does the actions as called out by the PF. But critically, these aren't rushed. Physical actions are typically deferred until the aircraft is stable, usually above 400 feet if it happens on takeoff, or once stabilized in cruise or descent.
Safety first, then actions.
Always. Once the immediate actions are done, the focus shifts to assessment. The next step is checking the status page on the ECAM display.
What does the status page tell them?
It's crucial. It gives an overview of the aircraft's technical state, what systems are working, what's failed, approach capabilities, and importantly, it directs them to any associated procedures in the QRH.
So it's a main dashboard for managing the ongoing failure.
Yes, and they'll be referring back to it constantly. The cognitive load here is immense. Step 3 is diving into those QRH summaries. Yeah, the QRH has summary sections specifically for handling major failures during different flight phases. Cruise, approach, landing, go-around. They'll use the cruise summary first to assess their situation, calculate the increased fuel burn, figure out landing distances based on the INRP systems.
This sounds like a continuous loop. Check status, check QRH, fly the plane, communicate.
It is. It's a dynamic management process, constantly reevaluating as they head towards the nearest suitable airport.
The procedure mentions that if the warning disappears, say, a generator comes back online, they should stop the procedure. How do they balance constantly checking systems and potentially stopping actions with the sheer focus needed to fly this compromised aircraft, especially during descent and approach?
That takes incredible discipline and crew resource management, CRM. It's all about that PF-PM split.
Yeah.
The pilot flying must dedicate almost 100% attention to maintaining control, speed, especially that 140-knot minimum, and the flight path.
So the PM takes on the rest.
The pilot monitoring carries the heavy load of checklist management, system monitoring, interpreting the status page, doing calculations, talking to ATC. They are the information hub, feeding critical updates to the PF without distracting from the primary task of flying. It demands seamless teamwork and communication.
Okay, let's bring it down to the runway. The final approach. What are the absolute must-dos, the non-negotiables for landing in ELEC EMER config?
The approach is very tightly constrained. Approach speed APPR SPD must be calculated as VREF plus 10 knots, but never less than 140 knots.
So VREF plus 10 or 140, whichever is higher.
Exactly. Got to keep that RAT spinning effectively. And the landing configuration is mandatory. Use ELTL 3, only flap 3.
Flap 3, not full flaps. That means a higher approach speed and less drag than normal.
Correct. It's a compromise.
Yeah.
Flap 3 is the highest flap setting that guarantees the availability of the essential flight controls needed given all the system losses. It ensures better handling qualities in the degraded state, even though it means a faster touchdown.
And there's that final stark warning about the landing roll.
Yes. As the aircraft decelerates through 50 knots on the runway,
Don't tell me.
all the display units go blank. Everything. Speed tape, altitude, engine indications, gone. Because the ACESS BUS sheds below 50 knots.
Wow, so they're finishing the landing roll, applying that limited manual braking, steering with differential brakes, effectively blind in terms of instrumentation.
For those final meters, yes. It's down to pure feel, external visual cues, and trust in the immense amount of training they've had for this exact moment.
So what does this all mean when you put it all together?
It means the ELEC EMER config isn't just another system failure drill. It's arguably the ultimate test of airmanship for an airline pilot. It strips away layers of automation we rely on, forces absolute adherence to strict physical limits, speed, braking, G-load, and puts everything back onto those core principles. Fly, navigate, communicate. It's the moment the advanced machine steps back and human skill, judgment, and teamwork have to take center stage entirely.
It really paints a picture of intense pressure and reliance on fundamental skills. From the R8 deploying to managing the descent while constantly checking systems to that incredibly high workload landing with minimal braking and instruments cutting out. It seems predicated on knowing the failure is likely permanent and time is critical. They commit to landing knowing the screens will go dark. What I'm left thinking about is the whole philosophy here about maximizing the remaining automation, or is it fundamentally forcing a reversion to raw manual flying, betting everything on the pilot's core ability? It just underscores how crucial that human element remains, even inside the most sophisticated automated cockpits flying today.